A mysterious place beneath the surface of Europe is manipulating the deepest laws of the universe, and it may change everything we've ever believed to be true. This is CERN, the research center where quantum physics is not just theory, but a gateway to a new reality beyond imagination. 1. Introduction to CERN and its role in quantum physics. In a place where particles smaller than atoms are accelerated to near the speed of light, a center of modern science is opening new doors for humanity to understand the nature of reality. This is CERN. When we gaze upon the starry night sky, questions about the origin of the universe, the structure of matter, and the nature of space-time have continuously driven human beings to explore. On that journey, a scientific organization located on the border between Switzerland and France has emerged as a global symbol of knowledge, CERN, or the European Organization for Nuclear Research. Though it gained fame for discovering the Higgs boson in 2012, CERN's influence goes far beyond fundamental particle physics, reaching deep into the realm of quantum physics, one of the most profound, mysterious, and challenging fields in all of modern science. What is CERN, where grandeur begins with infrastructure and intelligence? CERN, short for the French Conseil Européen pour la Recherche Nucléaire, was founded in 1954 as a symbol of scientific cooperation after World War II, beginning with 12 member states. Today, it has nearly 30 official member countries and dozens of partner nations across the world. CERN's original goal was to study the fundamental structure of matter, but over time, its scope has expanded into many branches of modern physics. One of CERN's most iconic symbols is the Large Hadron Collider, LHC, a 27-kilometer-long particle accelerator buried deep underground. This monumental engineering feat is where protons are accelerated to 9,999,991% the speed of light and smashed into each other, recreating conditions similar to those just moments after the Big Bang. But CERN is more than just a collision machine. It is a vast scientific ecosystem composed of thousands of researchers, engineers, technicians, and students from around the globe. CERN's role in quantum physics, the heart of the microscopic world. Although quantum physics is often associated with quantum mechanics at atomic and subatomic scales, many still mistakenly believe it exists only in theoretical labs or academic work. In reality, CERN is where quantum theories are made tangible through experimentation. By colliding particles at extremely high energies, scientists can test quantum hypotheses about symmetry, spin, dark energy, dark matter, and even extra dimensions. A clear example is the Higgs mechanism, a theory suggesting that the Higgs field interacts with other particles to endow them with mass. This is a cornerstone of the Standard Model of particle physics and is entirely based on quantum principles. The discovery of the Higgs boson at CERN was the first direct evidence that quantum predictions can indeed be verified through experiment, given the right technology and determination. Beyond the Higgs, experiments at CERN like ALICE, ATLAS, CMS, and LHCb continuously investigate microscopic phenomena related to quantum mechanics such as quantum decay, quantum tunneling, CPT symmetry, and much more. Physicists here are not merely confirming old theories but are constantly pushing the boundaries of human knowledge by testing hypotheses that go beyond the Standard Model, such as dark matter and dark energy, which are believed to make up over 95% of the universe but have yet to be directly observed. CERN, a convergence of global scientific excellence. It would be incomplete to talk about CERN without mentioning the global intellectual community it fosters. Every year, thousands of researchers from more than 100 countries come to work, study, and collaborate at this center. Here, political and linguistic borders dissolve. The sole objective is to pursue truth about the fundamental structure of the universe. This has turned CERN into a symbol not only of science but also of peace and international cooperation. Many Nobel Prize-winning scientists have worked with or collaborated with CERN. Generations of students and researchers trained here return to their home countries carrying with them knowledge, skills, and boundless inspiration. This is how CERN exerts global influence, not just through scientific publications but through people. CERN is also the birthplace of revolutionary technologies, most notably the World Wide Web, invented by Tim Berners-Lee in 1989 to support data sharing among scientists at CERN. Today, that technology has transformed how we live, learn, and work. A bridge between theoretical and experimental physics. One of CERN's greatest contributions to quantum physics is its ability to build a solid bridge between theory and experiment. While theoretical physicists like Richard Feynman, Niels Bohr, and Werner Heisenberg proposed revolutionary ideas about particle behavior, waves, and uncertainty principles, CERN is where those ideas are put to the test in reality. For instance, quantum mechanics proposes that particles can exist in superposition and that their behavior depends on the act of observation, a counterintuitive and difficult-to-believe concept. But at CERN, through particle collision experiments, such phenomena can be quantitatively measured. When a particle decays into multiple products, the probabilities and correlations among them can be described by quantum mathematics, and CERN's advanced sensors are sensitive enough to capture even the tiniest details. Another aspect is quantum field theory, which merges quantum mechanics with Einstein's special relativity. CERN is among the few places in the world capable of testing the predictions of this theory through high-energy particle collisions, thereby clarifying the relationship between energy, fields, and particles. The future of quantum physics is intertwined with CERN. Building on its strong foundations, CERN is moving toward even more ambitious goals. The high-luminosity LHC, HLLHC, upgrade project is expected to produce 10 times more data than the current setup, enhancing experiment precision and increasing the likelihood of discovering new physical phenomena. In the future, a new supercollider called the Future Circular Collider, FCC, with a circumference of up to 100 kilometers, is being proposed to achieve collision energies many times greater than those of the LHC. With advances in quantum computing and AI, CERN is also stepping into the realm of quantum-scale data analysis like never before. Using machine learning algorithms to search for rare events among billions of collisions per second is becoming a reality. More importantly, CERN is taking the lead in inspiring the next generation of scientists. CERN is not a quiet place of abstract theories. It is a beacon of science, a symbol of international collaboration, and a terminal station on the journey to uncover the deepest mysteries of the universe. Conclusion. CERN is not merely a particle physics research facility, but a global hub of intelligence, technology, and scientific ambition. Playing a key role in verifying and developing quantum physics theories, CERN has profoundly changed how we understand reality. From confirming the existence of fundamental particles to studying phenomena like quantum entanglement, superposition, and uncertainty, CERN continues to expand the boundaries of human knowledge. The road ahead is long, and many quantum mysteries remain unsolved. But if there is one place on Earth capable of unveiling the seemingly unseeable, it is CERN, the beating heart of global quantum physics. 2. Events at CERN related to quantum physics. When the laws of classical physics are no longer sufficient to explain the strange phenomena in the subatomic world, it is at CERN that cutting-edge events and experiments have been organized to unveil the secrets of quantum physics, from theory to experimentation, from bold hypotheses to discoveries that redefine human perception. If the previous section depicted CERN as a magnificent machine driven by modern intellect and technology, this part is the living heartbeat of that very machine. CERN is not only a place that provides infrastructure for research but also the epicenter of historical milestones in quantum physics. Scientific announcements, symposiums, large-scale experiments, and academic forums have marked major turning points in humanity's understanding of the microcosm. The Higgs boson announcement, a defining moment. July 4, 2012, entered the annals of modern scientific history. In CERN's main auditorium, thousands of scientists, journalists, and representatives from leading institutions around the world gathered to witness a groundbreaking announcement, the discovery of a particle consistent with the Higgs boson. This experiment was conducted through two large detectors, ATLAS and CMS, of the Large Hadron Collider, LHC. The Higgs boson is an indispensable piece in the standard model of particle physics. Its existence explains why fundamental particles have mass. From a quantum perspective, the Higgs field permeates the universe, and as particles interact with this field, they acquire their mass. Prior to this moment, it was only a theoretical hypothesis. But thanks to CERN's technology and massive international collaboration, that hypothesis became reality. The announcement of the Higgs boson was not only a victory for particle physics but also a testament to the power of quantum physics. It proved that quantum models can predict with astonishing precision phenomena in a world invisible to the naked eye. Quantum Cosmology Conference at CERN, where physics meets philosophy. In recent years, CERN has organized numerous large-scale symposiums focused on quantum cosmology, a research area connecting quantum physics with cosmology and general relativity. One of the most prominent events was the Quantum Universe series of conferences, which brought together leading scientists such as Carlo Rovelli, Juan Meldacena, and Abhay Ashtekar. At these conferences, age-old yet profoundly philosophical questions were discussed from both theoretical and experimental perspectives: the origin of time, the nature of space, and whether the universe itself is a giant quantum phenomenon. Models such as cyclic cosmology, loop quantum gravity, and multidimensional universes were hotly debated. Particularly intriguing and controversial was the relationship between quantum information and entropy in black holes. These conferences are not just academic exchanges but also a source of inspiration for both the research community and the public. They serve as a meeting point where science and the nature of reality converge, and CERN acts as a bridge between bold ideas and experimental grounding. The LHCb experiment and asymmetries in the universe. Equally significant are the experiments under the LHCb, Large Hadron Collider Beauty, project, which focuses on particles containing bottom quarks, one of the 6 fundamental types of quarks. A major question in modern physics is why the universe contains more matter than antimatter, even though theory suggests they should have been produced in equal quantities after the Big Bang. The LHCb experiment aims to investigate CP violation, charge parity symmetry, one of the potential explanations for the matter-antimatter imbalance. CP violation is a subtle quantum effect observable only with ultra-precise instruments and massive datasets, both of which CERN supplies in abundance. The accomplishments of LHCb go beyond confirming known CP violations; they open new possibilities for phenomena not yet described in the standard model. Scientists hope that by analyzing particle decays and even the smallest deviations in data, they may uncover clues about dark matter and new fundamental forces. Workshops on quantum entanglement and quantum information. CERN has also embraced the rapidly growing field of quantum information. A series of workshops and conferences on quantum entanglement have been organized, focusing on how particles can exhibit non-local correlations, a phenomenon that Einstein once called spooky action at a distance. These workshops bring together experts from leading institutions like MIT, Caltech, the Perimeter Institute, and major European universities. Topics discussed include quantum teleportation, distributed quantum networks, quantum algorithms, and the relationship between quantum entanglement and the structure of spacetime. Notably, some scientists at CERN are proposing that the three-dimensional space we live in may itself emerge from a microscopic network of quantum entanglement. This idea could lead to a revolutionary shift in our understanding of reality, that space is not merely the stage on which physical phenomena occur, but a product of quantum phenomena itself. The NA62 experiment and the search for exotic matter. Another notable event is the NA62 experiment at CERN, designed to study the rare decays of kaon particles. These decays are extremely improbable but may carry clues about the existence of particles never before detected, such as axions or heavy neutral leptons. From a quantum physics perspective, kaon decays clearly demonstrate quantum uncertainty and superposition. Observing these rare decays is evidence of quantum interactions that can only be seen through billions of collisions. The NA62 research team includes scientists from over 20 countries, with participants from major institutions like the Max Planck Institute, Fermilab, and JNR. This is clear proof that CERN is not solely focused on common particles like protons or electrons, but is also willing to search for extremely rare particles, potential keys to theories beyond the standard model. Quantum Technologies Forum at CERN. In an effort to bridge fundamental research and technological applications, CERN has hosted the Quantum Technologies Forum, with participation from businesses, research institutes, and governments from various countries. Topics presented include quantum sensors, secure communication networks using entangled photons, quantum computing, and quantum cryptography. CERN is also developing particle detectors based on quantum effects to increase the precision of future experiments. The convergence of quantum technology and particle physics is gradually forming a new interdisciplinary scientific field, where each discovery can lead to practical applications in medicine, security, aerospace, and communications. The caliber of speakers and the academic community at CERN. A common thread across all events, conferences, and experiments at CERN is the participation of the world's brightest minds. Nobel laureates such as Gerard T. Hooft, Frank Wilczek, and the late Steven Weinberg have all taught or made academic contributions here. Additionally, major organizations like the Kavli Institute for Theoretical Physics, the European Physical Society, and the Clay Mathematics Institute regularly send representatives to key events at CERN. Besides seasoned researchers, younger generations are also given opportunities through programs like the CERN Summer School, the International Postdoc Program, and various research competitions. This creates a multi-layered environment where knowledge is not only shared but also inherited and advanced. Conclusion. Every event at CERN, from specialized conferences to massive experiments, represents a new rung on the ladder of quantum physics exploration. These are not merely academic activities, they are catalysts driving the advancement of global science. They shape research directions, lay the groundwork for future technologies, and above all, ignite faith in humanity's boundless capacity for understanding. CERN does not merely observe the universe, it recreates its smallest building blocks, striving to construct a more complete picture of reality. And the events held here, without a doubt, are the beacons lighting the way forward in our quantum age. 3. What is quantum entanglement and its role in research at CERN? As science approaches the boundary between classical perspectives and the quantum horizon, the phenomenon of quantum entanglement not only shakes traditional notions of causality but also opens new doors to revolutionary research at CERN, a place where reality is no longer taken for granted but is something that must be proven layer by layer. Following groundbreaking achievements in particle research and historical discoveries such as the Higgs boson, CERN has not stopped at recreating the conditions of the early universe but has delved into a phenomenon that Einstein once described as spooky action at a distance, quantum entanglement. This is not merely a paradoxical physical phenomenon but a key to deeper understanding of the structure of spacetime, the nature of information, and the mysterious interconnectedness of the universe. Quantum entanglement, the transcendent relationship between particles. At the quantum level, particles can be created in such a way that their states cannot be described independently. They form a connected system, where the state of one particle instantly reflects the state of the other, regardless of the spatial distance between them. This is what we call quantum entanglement. Unlike classical correlations, quantum entanglement is not limited by the speed of light. Even if entangled particles are separated by millions of kilometers, changing the state of one immediately results in a corresponding change in the other. This not only challenges our current understanding of spacetime but also raises profound questions about the existence of an objective reality independent of observation. A pillar of modern physics. Over the past decades, quantum entanglement has moved beyond theoretical frameworks to become a cornerstone of the most advanced areas of modern research, from quantum computing and quantum cryptography to modeling information in black holes. Entanglement is not only a technological tool but a test of humanity's understanding of the microscopic world. In particular, the Bell test experiments, designed to verify the non-local nature of the quantum world, have confirmed the predictions of quantum physics, while local hidden variable theories have been rejected. These experiments are not merely theoretical validations, they are evidence of a universe in which all points in space may be linked by invisible threads beyond classical intuition. CERN and the mission beyond particles, quantum entanglement in a broader context. Although widely known for its particle accelerator experiments, CERN is not simply a place for proton collisions. In the context of quantum entanglement, CERN plays a key role in three areas: testing non-locality, studying entanglement's role in cosmological dynamics, and exploring the relationship between entanglement and the structure of spacetime. One line of research at CERN involves conducting Bell tests with particles produced in proton-proton collisions. By analyzing correlations between the generated particle pairs, scientists verify whether these interactions are non-local, as predicted by quantum mechanics. Performing Bell tests in high-energy environments like CERN helps extend verification beyond simple optical systems, bringing quantum entanglement from small labs into extreme real-world physics. Quantum entanglement and information in black holes. A particularly intriguing area of study is the relationship between quantum entanglement and information conservation in black holes. At CERN, workshops such as black hole information and quantum entanglement have examined the question: does information vanish when an object falls into a black hole, or is it preserved through some form of entanglement? New models, such as the holographic principle or the firewall paradox, require a deep understanding of quantum entanglement to explain interactions between matter, space, and time under extreme conditions. With powerful theoretical tools like string theory and the ADS/CFT correspondence, researchers at CERN are contributing to shaping a theory of quantum gravity, an effort to unify quantum mechanics with general relativity. Quantum entanglement as the structure of spacetime. Some scientists at CERN and their collaborators are pursuing a radical hypothesis, that spacetime itself is not a static backdrop but an emergent phenomenon arising from quantum correlations between fundamental elements. According to this approach, the quantum entanglement network could be the true foundation of the universe. As the degree of entanglement changes, the structure of spacetime may expand, warp, or even branch. This idea is not only philosophical but also suggests experimental directions. At CERN, some projects are searching for quantum signatures in the cosmic microwave background or statistical anomalies in particle collision data. Finding evidence of a link between quantum entanglement and the structure of spacetime could become one of the most significant discoveries of the century. Practical applications: quantum computing and quantum sensors at CERN. Quantum entanglement is not limited to theoretical domains, it is also being harnessed to develop cutting-edge technologies at CERN. In satellite labs, CERN is testing ultra-sensitive quantum sensors that use entanglement to enhance precision in measuring magnetic fields, temperature, and vibrations. These sensors can be integrated into particle detectors to improve accuracy and expand detection thresholds. CERN is also experimenting with linking to prototype quantum computers to analyze collision data. Processing hundreds of petabytes of data from detectors such as ATLAS and CMS requires not just computing power but also quantum algorithms that can exploit entangled states to perform multiple measurements simultaneously. International collaboration on quantum entanglement research. Quantum entanglement research at CERN does not occur in isolation. The organization collaborates closely with leading institutes such as the Niels Bohr Institute, the Max Planck Center for Quantum Physics, and research programs from Caltech, Princeton, and ETH Zurich. Through academic exchanges, international conferences, and joint projects like OpenQCD, CERN has become a central hub for fundamental quantum research. Moreover, CERN is one of the key partners in the European Quantum Technology Alliance, which is developing a quantum information distribution network across the continent. Quantum entanglement plays a core role in secure information transmission, and the experiments at CERN are early steps toward realizing global quantum networks. A new perspective on reality. Once thought to be purely fantastical, quantum entanglement is now reshaping the map of human knowledge. At CERN, entanglement is not only a strange manifestation of quantum mechanics but also a tool for exploration, a subject for theorization, and the foundation for future technologies. The story of quantum entanglement at CERN is a fusion of classical knowledge and visionary thinking, of precise experimentation and scientific imagination. From entangled photon chains in detectors to hypotheses about space emerging from quantum networks, all point to the fact that we have only just begun to scratch the surface of a deep and metaphysically connected reality. Conclusion. In the quest to uncover the ultimate nature of matter, energy, and spacetime, quantum entanglement serves as a guiding light, leading physicists through the infinite maze of particles and fields. At CERN, where the collective intellect of humanity converges at an unprecedented scale, research into quantum entanglement not only validates crucial theories but also fosters a new way of thinking, where the boundaries between space and information, physics and philosophy, begin to dissolve. Beneath every collision, every data chart, every line of analysis code at CERN lies a message from the quantum world: reality may be stranger than anything we've ever imagined. And in the hands of CERN's great minds, quantum entanglement is the key to unlocking that world. 4. The impact and future potential of quantum research at CERN. As quantum-level discoveries continue to shatter the boundaries of human perception, CERN not only serves as a place where the deepest layers of reality are observed, but also as a launchpad for humanity's future, in science, technology, and our understanding of the universe. Following a journey through the history of fundamental particle research, high-energy collisions, and quantum entanglement, we now witness another turning point, from pure understanding to practical application, from hypothesis to verification, from theoretical analysis to shaping the future. At the world's largest research center, every measurement taken, every system installed, every computer program run carries the mission of redefining modern physics and guiding humanity into a new era. Contribution to fundamental science, where theoretical frontiers are tested and expanded. Unlike typical research centers, CERN plays a pivotal role in challenging, testing, and reconstructing physical theories. It not only confirms the existence of particles like the Higgs boson but also sheds light on abstract concepts such as symmetry, supersymmetry, the indivisibility of space, and quantum vacuum decay. Research at CERN enables verification of theories like the Standard Model, while also pushing beyond its limits. By generating and analyzing extreme conditions, physicists can assess the accuracy of theoretical predictions. When experimental results diverge from theoretical models, it is a valuable signal pointing toward new research directions. In the quantum realm, CERN helps reshape physical laws through detailed analysis of entangled particle behavior, weak interactions, and neutrino oscillations, all of which are essential building blocks of post-standard model physics. CERN is the place where theory meets reality, and when the two no longer align, new truths are born. From blackboard to application, quantum technology and everyday life. Where quantum physics once existed only in abstract lectures, today, thanks to research at CERN and its partners, those elusive concepts are becoming real-world technologies: quantum communication, quantum computing, quantum sensing, and photonic information processing. Absolutely secure communication. One of the most promising applications is the quantum information network. With quantum entanglement, researchers at CERN and the European Quantum Technology Alliance are developing communication systems that are immune to eavesdropping. Due to properties like non-clonability and measurement disturbance, quantum information offers unparalleled security, a key feature sought by financial, defense, and healthcare sectors. Quantum computing for collision data. The LHC generates hundreds of millions of collisions per second, and detectors such as ATLAS and CMS collect massive amounts of data, hundreds of petabytes each year. Classical computing struggles to process such volumes. That's why CERN is investing in projects that interface with quantum computers to run physics simulations, analyze models, and optimize detector design. Collision data is processed using entanglement and superposition to evaluate thousands of scenarios simultaneously, something classical computers cannot achieve. Quantum sensors for medicine and earth science. Beyond physics research, CERN is also developing ultrasensitive quantum sensors to measure magnetic fields and minute vibrations. In medicine, this translates to more accurate imaging, early cancer detection, and radiation targeting that spares healthy tissue. Another promising direction is quantum seismology, where sensors can detect underground movement hours earlier than traditional methods, enabling more accurate earthquake prediction. CERN's expansion projects, the beginning of a new cycle of discovery. Far from remaining static, CERN continuously expands its research scope through long-term visionary projects. High Luminosity LHC, HLLHC. The HLLHC project is an effort to upgrade the LHC's beam luminosity by a factor of 10. The goal is not only to collect more data but also to detect rarer, weaker, and harder to identify particles. This opens the door to investigating physics beyond the standard model, such as dark matter, supersymmetric particles, and previously unobserved states. Future Circular Collider, FCC. Planned as the successor to the LHC, the FCC would be the largest particle accelerator ever built, with a circumference of about 100 kilometers. It would allow scientists to collide electron-positron and proton-proton beams at much higher energies. This promises to test new theories such as extra dimensions, micro-black holes, and quantum gravity interactions at the particle scale. Quantum Technology Initiative, QTI. Alongside accelerator development, CERN has officially launched its Quantum Technology Initiative, QTI. An international program aimed at accelerating applications of entanglement, superposition, and decoherence in practical fields. QTI focuses on building platforms for quantum measurement devices, enhancing quantum simulation, and developing quantum chips. Impact on philosophy and our understanding of reality. Quantum research at CERN does not stop at science and technology, it also reopens fundamental philosophical questions. Does the world exist independently of the observer? Are space and time objective entities, or manifestations of quantum entanglement? Does human perception affect physical states? Phenomena such as entanglement, non-locality, and the measurement effect have led scholars to recognize that knowledge is not just about observation but involves active human participation in shaping the universe's structure. This recalls the insights of ancient philosophers while opening new approaches in modern epistemology and ontology. The quantum future. A door not yet fully opened. Looking ahead, CERN's quantum journey is only just beginning. As detectors grow more sensitive, accelerators more powerful, and analytical tools more intelligent, we approach the ultimate frontier, where physics, philosophy, and metaphysics converge. Future projects include ultra-precise quantum clocks to measure spacetime curvature, planet-scale entangled networks, and even hypotheses about parallel universes, all currently under discussion within CERN. If successful, these could help humanity rewrite the first chapters of the universe's history, not just with equations, but with profound insights into the role of information, consciousness, and the fabric of reality. Conclusion: CERN and the Quiet Revolution. While much of the world races with the pace of technological inventions, scientists at CERN are carrying out a quiet revolution, one that not only transforms our understanding of the universe but also how we exist within it. Through research that spans from foundational quantum theory to real-world applications, from entanglement to black hole information, CERN is becoming the beating heart of modern science. What happens here is not the end, it is the beginning of a new era, where every boundary can be transcended if we dare to look deeply into the quantum world and accept that reality may be entirely different from what we once believed. The universe we live in may be stranger than any science fiction story ever told. And it is at CERN where these silent secrets are gradually being uncovered, experiment by experiment, collision by collision, each tiny particle challenging the entirety of human understanding. If you find the quantum world to be a maze that is both mysterious and mesmerizing, leave a comment below and join us on this journey of discovery. What do you think will be the next major turning point in quantum physics? And are we truly ready to face a reality that might be completely different from everything we've ever known? Don't forget to subscribe to Forbidden Knowledge and turn on notifications so you won't miss any videos that push the boundary between science and the unknown. Thank you for joining us on this voyage into the heart of the universe. See you in the next video.